Got the time pick. No? Thanks. All right. So, yeah, let's go over this and sort of what comes up in this proof. So, again, we have V and C star to the n. Is algebraic. So assume that the torsion points inside V are the risk index in V. And let's assume that V is not contained in a subtorus of C star to the n. V is not contained in a torsion coset, proper torsion coset. Okay, assume V is not contained in a proper torsion coset. And we would, so n is not equal to C star to the n. So we want to conclude some contradiction from this. Get Langsdorff contradiction. Okay, so let's just make a simple reduction. So since V is not contained in the proper torsion coset, it actually can't be contained in the torus coset, right? Because if V torsion is not empty, it will contain the torus coset, it will be contained in the torsion coset. So therefore, V is not contained in a proper torsion coset. And so as a result of this, as we saw sort of a while ago, maybe a month or so ago, the image of pi 1v in C to the n, which is the monodromy of C star to the n, is finite index. Is image of finite index. This would be an important point for us, more so than last time even. Okay, so now let's bring in the O minimal picture. Okay, so now we look at sort of, let me call it pi. From C to the n to C star to the n. I want to exponentiate every coordinate, scaled by 2 pi I. We'll call that okay. So this is the information map. And we'll define F and C to be fundamental domain. Again, you gotta be a bit careful with less than, bigger than, but with the, this is less than or equal to, or this is less than or equal to, but that's not a big deal, it's sort of an annoyance. So we'll just deal with this fundamental domain. And as we observed before, if you restrict pi to f to the n, then this function is definable in Rn(x). So now we can play with it and get things definable inside Rn(x). Okay, so how do we make use of this? What we do is we first take V0 to be the kinetic component of pi inverse B, so we pull V back. By assumption it gets finitely many kinetic components, because monodromy is image which is finite index. So let this be the connected component, the A component say intersecting F to the N. Okay? And so note, as a consequence of pi being definable on F to the N, if we look at pi inverse V and intersect with F to the N, then this is a definable set in R and X. Right, because we're pulling back V, which is definable in here, under a definable function, which is pi with F to the N. This is definable. Now I'm going to stop writing in R and X. We're only ever going to work with R and X from now on. The only field that number theorists have decided they must know. On the structure. Okay, so this is definable in R and X. Great. And so now, we need Galois orbits input. So now we're going to use large Galois orbits. Okay. So saw that if Z, well, I guess let me downstairs use coordinates that are a bit different. So let's say if Q1, Qn in V is a torsion point of order M, Q, and the Galois orbit of this is of size phi of n, which is bigger than, say, square root of n. It's better, but it doesn't matter. We just need any positive power, square root of m, positives. Okay. Oh, so I guess I didn't make this reduction, but so we're going to assume that V is defined over Q in the same way we did before. Okay. We want Galois orbits. Okay. Then is of size phi of m is at least square root of m. And so if you look at pi inverse V, intersect F to the N, and this contains phi of n rational points. They're actually rational in this case of height at most m. Right? In fact, exactly m, because you have, if you pull back under pi, under the E map, I guess, root of unity of order exactly m, you get something of the form a over m. Is that our main fundamental domain? That's a rational number of height at most m. Okay, so this guy contains rational points. Okay, so my assumption is torsion points, there's many of them, in fact they're risky dense. So let me say, by assumption, V contains is a risky dense set of such points Q, let's say I or whatever. And so pi inverse V sec f to the n contains semi-algebraic varieties containing all, containing all but finitely many, all but sub-polynomially many of these points. Right, where at this point we're invoking the Pila-Wilke theorem. So V contains tons of these points. For each one, pi inverse V to the n. Look at guys with height m. You already contain root and point from a single Galois orbit. So take this is true for infinitely many m, which means that this definable set contains more than sub-polynomially many points. Right? It's not true the number of points of height t is the most of the epsilon. It's not true it's the most of the 1/2. So by Pila-Wilke, it contains some semi-algebraic curves. Okay? So as a result, let's say this contains at least one semi-algebraic curve W. Okay, so that's the first step. We sort of have this argument, the pre-image, variety downstairs contains a semi-algebraic curve upstairs. Okay, so now there's one minor annoyance to deal with, which is, there's many minor annoyances to deal with, but the first one that comes up is that if you, so what does this mean? You know, semi-algebraic structures are a real thing, like the whole theory is a real theory. So we have a complex analytic set, pi inverse V, which is sort of, inside here is definable, but other than that, just a holomorphic set, an analytic set. But it contains a real semi-algebraic curve W. And real guys are sort of much less clean, holomorphic guys. And what we really want to do is upgrade this W to be a complex algebraic curve. Okay. So we have this sort of fairly straightforward lemma. So let's say V, let me call it something different. So let's say A C to the N is an analytic set defined by vanishing polymorphic functions everywhere. and C in A is a real semi-algebraic curve. Then A contains a complex algebraic curve. Let's call it D containing C. So actually more is true, but let's just start with this, get the idea. So I'm sure there's like thousands of proofs of this. Here's one of them. So C is a one-dimensional real thing. So let P and C be a smooth point. And the dual log assume that x1 is not sort of constant on C at P. So x1 is locally sort of a real algebraic coordinate up to a finite amount. So what does this mean? So note that like C to the n, what are coordinates on it? There's z1 through zn. And so real coordinates on it are x1 through xn together with y1 through yn. Okay? So what does this mean? So then, if you look at any j between 2 and n, then xj and x1 are algebraically dependent on C. You can also do it with the y's, but then we stick to the x's. So we have some polynomial qj such that this is 0. And C, at least at P, and qj is a polynomial of two variables. Right? So now let D be the zero set of all of these guys. So let me write this as x1 plus iy1 and xj plus iyj is equal to 0. Okay? So D is the vanishing locus of all of these guys. Okay, so then D is an algebraic curve because for every variable that's not z1, we're giving it an algebraic, a non-vanishing algebraic equation over z1. So z1 is the local coordinate on D. So then D is an algebraic curve. Right. So again, did I mess this up again? I may have. Yeah, the segment, for some reason I find it very subtle. Whenever I write it down, it ends up being wrong in the end. So So I want to say that it's 0 here. I want to say it contains C, but I think I screwed up. So give me 1 second to fix it, and then I'll rename again. Sorry, yeah, I meant to. Yeah, I'm sorry. I didn't actually mean this. Everywhere here I meant Z. So, yeah. Right. Sorry, the point is x1 is not constant, so x1 plus iy1 is also not constant. So you deal with these guys from the very beginning. Yes. Okay, this makes much more sense. Sorry about that. Let me go over the argument again very quickly. So we start with the real coordinate that's not constant. And then because if x1 is not constant, certainly x1 plus iy1 is not constant, because the real part is x1. Okay, now you have two functions on this algebraic curve, two algebraic functions. They're complex values, but it doesn't sort of hurt anybody. So all the same stuff is true. There's some polynomial which vanishes, which creates the dependence of these two functions. And now you just consider this sort of polynomial in general. The point is, because we're stuck in holomorphic guys here, this ends up being an actual holomorphic curve. Okay. So D is an algebraic curve containing C. And if you look at D intersect A, then this is infinite around P, because it has real dimension. Now you have an analytic set, but analytic sets at a point of dimension 0, 1, 2 or something. So this can't have dimension 0, so infinite many points around P. So in particular, P can't be isolated, so therefore A has to contain B. That's right. Okay. Does the argument make sense? I mean, the basic idea is you have tons of real algebraic guys you can create, and you just look for them. Look for the ones which happen to be holomorphic. And define some holomorphic variety, and then you're set. Okay. Okay. So, point is, we started with a real algebraic curve inside a pre-image, and we ended up with a complex algebraic curve. And so, another reason this is nice is because complex algebraic curves are a global object, and as mean holomorphic continuation. So if they're inside some analytic set to begin with, they're inside for all time. Okay? Okay, so basically we have pi inverse V, which is globally analytic, contains a complex algebraic curve, which I'm going to call W. Okay? So this is for bookkeeping, let's just assume that W is inside V0, which is fundamental domain, so some component of, let's say, V0. Okay, and so now we have to study this question, which ends up being a classical question. We'll talk about it later. But we have this sort of transcendental map pi, and we have an algebraic guy downstairs, and its pre-image contains an algebraic guy upstairs. Okay. So earlier we talked about, I think we did the case where it's algebraic downstairs and upstairs, and then it has to be a torus, just by a monodromy argument. It's got to be invariant by too much stuff, not be a torus. This ends up being substantially harder if W is just contained inside V0, because you can't sort of, I don't know, they're sort of independent of each other. So this ends up being sort of a crucial step in this whole argument. And so in this case, this has been dubbed the X-Lindemann-Wire stress theorem. Even though X only proves the stronger statement to begin with, which implied does. It does follow from it. Which says that if V in C star to the n and W in C to the n are algebraic, and W is in the pre-image of V, then there exists, we can say it two different ways, up to or downstairs. Let me say upstairs. A Q-linear subspace, let me say a coset of a Q-linear subspace L in C to the n. So a linear subspace with rational slopes, but possibly a translation of it, such that L sort of lies between W and V. It allows for addition between them. So W is in L, which is in pi inverse of V. Okay? Another way to say is there exists a torus coset downstairs, which is contained in V, such that its pre-image contains W. That ends up being identical. Okay? So sort of the idea being that, if you wanted to construct the situation, how could you do it? Well, you could just take a torus coset downstairs, which is a Q-linear subspace upstairs, and they're both algebraic, so that's sort of good. And now obviously you can take any V containing the image of that, containing that torus coset, and any W inside its pre-image, and you'll still have this relation, because you've only made this bigger and this smaller. And so the theorem is that it's the only way that you can make this happen. Okay. Okay. Yeah, so originally X proved this by looking at the exponential function and using this differential equation and doing a bunch of cool algebra. So I want to give the minimal proof that was given by I think by Pila actually. I think Pila and Zani just quoted X when they were doing their stuff. Okay, so here we're going to use the. So yeah, a really cool feature of this proof is that we've already used the omnimality when using Pila-Wilke, right? We got some definable set in RNA containing many points. We got something algebraic thing. We needed omnimality for that. We're not going to use it again in a totally separate part of the argument, which is this transcendence thing. Before you're right to do with omnimality, but it ends up being a really useful tool. So, okay, so again, so suppose that V naught in V is such that V naught contains W and V naught intersects. So and let me say sort of that. Yeah, V naught intersects. V naught by I'm sorry. Intersects F to the n. Or maybe let's say just assume W intersects F to the n. Sure. Okay, so we have this set up, and so what's the idea? The idea is very much going to be the monotony. Let me give the idea and then I'll give the formal sort of construction. So the idea is that for gamma in so let's write gamma to be the image of pi 1v in z to the n. So it's the monodromy group of v. And so then for gamma, little gamma in big gamma, little gamma times v naught is equal to v naught. Right? So little gamma times w is another. So how does little gamma act? Just x by translation, right? I'm writing it this way, but gamma times something is literally just that something translated by some integers. Gamma times w is another algebraic variety contained in V naught. So all of a sudden we have sort of a lot of algebraic varieties contained in V naught. So the idea is to use this fact and do it by defining the following clever set. So you look at all t in C to the n. So what we try to say is such that t plus w, well, t acting on w, well, maybe for simplicity I should write plus. I'm confusing myself otherwise. The monodromy group does act by translation. Let me just do that. Such that w plus t is contained in V naught. Okay, but we could do this, but this wouldn't be definable if we defined it this way, because V naught is not a definable object. Only V naught intersect fundamental domain is a definable object. So we do something a little bit different. We look at this, intersect f to the n. We insist that that is contained in V naught intersect f to the n. So this is fine, because now everything inside is a definable object. So it could intersect like this. Okay, but now this is a little bit too weak, because this set can be empty, and being empty is a good way to be contained in something. So we want to avoid that, because that's sort of cheating. And so we also insist that, w plus t intersect f to the n, it's enough to just say it's not empty. Being not empty, w we can assume is irreducible, and then this already insists that it has the correct dimension inside here. Okay? Okay, so we define this set, and then the upshot is that I is definable. It's a subset of C to the n, because everything inside that we're talking about is definable. Is that sort of clear, everyone, that this is definable? Any part of it? Like we're just sort of doing, containment's easy, it's like for all, something in here, it's in there, not empty is easy. Intersecting and acting is also easy, so everything is sort of straightforward. That's it. Yeah, it takes a while to get used to. Okay, so what sort of, let me draw a picture I find helpful. So a good way to think about it is sort of, let's imagine that one of these squares is up to the n. So in this case, n equals 2, and I'm only drawing the real part, but whatever. So one of these squares is like a fundamental domain, and then bordering it, you have a bunch of other fundamental domains, either the integers that sort of covers all of c to the n. Right? Now inside here, you have w. Let's say w somehow does something like this. Okay? Now w stays inside v naught for all time. So this whole thing is inside v naught. Moreover, whenever w enters one of these squares, right, if we then shift to bring that square back to f to the n, then we get a translation of w, which intersects f to the n, and is also contained inside v naught. Because let's assume v naught is invariant under the entire thing. Yeah. We shift it, we get something. The image contained inside v naught. Okay. So I think, to make the argument work, you can't quite do this. You got to do all of pi inverse v, I think. Let's put all of pi inverse v over there. Okay, so now in order to get this I containing many different points, what we have to show is that W goes through many of these fundamental domains. That will give I many integer points. And so first of all, it will give I it's kind of straight how this goes. So I is a definable thing. So if it contains infinitely many points, period, it has to have dimension because of cell decomposition. So I will automatically be some analytically dimensional set. But we sort of want more. We want I to be algebraic, or to contain algebraic things. Okay, so we want for it to have actually many integer points. So the idea is to show W passes through many fundamental domains so that the integer points of I is big. Being infinite, but also grows pretty quickly. Okay, so first of all, claim W passes through infinitely many sort of fundamental domains. I.e., what I really mean by this is that IV is infinite. Okay? So W can't just stay inside one of these guys and find many of these guys. Okay, so the proof is actually really obvious. W is algebraic, so Z1 maps onto C, except when we do this function many points. So the real part can't be contained inside any of these guys. Okay, so the proof is that like Z1 from W complex numbers is an algebraic function. And so, let me erase W. I'll put it back up later when we need it. So if Z1 is not constant on W, the image of Z1 in C is cofinite. Okay? Whereas in each fundamental domain, the image of Z1, the real part at least, is bounded. It's contained in some interval 0, 1, or n plus 1 in general. Okay? Okay, so now 1 of Z1, Z2, Zn, material to W is not constant. For sure. Right? They're all constant in W, good point. That's not good. One of them is not constant, and so yeah, so that's it. Okay. Let me just go just a couple minutes over, or that clock is a little fast, yeah. So another claim. So this claim actually makes this story significantly simpler than we're going to have to deal with for the modular case. Is that automatically, as a corollary of this, a corollary, IZ actually grows polynomially. So, in fact, the number of points in IZ of height t grows linearly in t. Okay. So the proof is very simple, is that W is connected, just as a set, pathwise connected. So you actually can't jump out of these squares very quickly, right? So IZ inside Z to the n forms a connected graph. Right? Where the edges are the obvious one. We just add, you can change a coordinate by 1 every time. This box can only sort of go to these boxes. So okay, but so you can't jump out of a box of height t without going through at least 2 different points. Okay, so I'll leave this as an exercise. But so I hope it's sort of clear. You know, if you want to get out of here where t equals 4 and you start here, you have to, the fastest you can do is just sort of jump up with one coordinate as fast as you can. Okay, so IZ is definable and it contains many. I is definable, sorry, and it contains many integer points, so it contains some semi-algebraic stuff. Alright, let's continue next time.